Hey, Mr. Sams.
Yes.
Yeah, I've been thinking maybe I should make another career change.
Oh yeah, no more music?
No, I'm thinking no more music. Sorry, on the music there. Yeah, I got the harmonic here.
Okay.
No.
Yeah.
It works, you know.
Better than the other ones.
But I was thinking, maybe I should become like an inspirational speaker.
Oh, motivational speaker. Okay.
Yeah.
Get hired out to go get people fired up to do something or other.
Yeah, and I've heard that they always kind of come up with really good one-liners.
Okay. Yeah. Usually.
Yeah, like this one.
Okay.
I told my doctor I broke my leg in 2 places. You know what he told me?
Huh.
Quit going to those places.
Oh, yeah. That's inspirational. Very.
And then last night, I went in bed looking up at the stars in the sky, and I thought to myself, where the heck is my ceiling?
Yeah. That's probably something you should think about if you're lying in bed and you're seeing the stars. Yeah.
Or this one, the greatest thing or pleasure in life is doing what people say you cannot do.
Now that's definitely something you could probably hear from motivational speakers.
Yeah. So maybe I should become a motivational speaker.
Yeah, maybe. I don't know.
Mr. Bergman, the motivational speaker. Got my podium, right? Stand up in front of a audience.
There you go.
There's my audience. I guess I do have an audience, though.
Or you could live in a van down by the river.
Oh, I could be a van down by the river. What's that mean?
That's another Saturday Night Live sketch. That's Chris Farley.
Oh, Chris Farley.
He was the motivational speaker, but he lived in a van down by the river.
Oh, I see.
Yeah.
Okay.
Yeah, that's good.
Well, hey, we're going to do Chapter 6 today.
Yep.
And we're going to learn about thermochemistry. What's that mean, thermochemistry?
Thermo looks like heat and chemistry.
So we're going to be studying the chemistry of heat. All right? Yeah, probably I'll stick to this because I know a lot about chemistry. I don't know a lot about motivational speaking. But, I might give it a shot, I'll come up with some more quotes. Yeah.
All right.
Hey, what do we know about thermodynamics?
Energy, it cannot be created nor can it be destroyed.
Cannot be created or destroyed.
And that is called the law of conservation of energy.
And also called the first law of
thermodynamics.
Thermodynamics.
Yep.
There's another word, thermodynamics. We'll learn more about that in the year. Hey, and the sum total energy is in the universe is what?
I'm assuming you mean constant.
Constant.
Yeah.
It doesn't change. So it is a constant amount, and it does not change. And now, this word thermodynamics, actually, let's break it apart. The word thermo, of course, we kind of talked about this already. Thermo means heat. And what's the word dynamics mean?
Usually a change.
Yeah, it talks really about movement.
Yeah.
The word a dynamo is something that moves.
Mm-hmm.
Somebody who's dynamic is probably moving around as he speaks. The
motivational speaker!
So we have movement. So hey, we're studying how heat moves.
There it is.
Can heat move?
Mm-hmm.
What do you mean it moves? How does it go?
It has to go from one place to another, and it goes from an area of a higher temperature to an area of lower temperature.
Yes, it does. So we're going from a high temperature to a lower temperature.
So yeah, there's no such thing as cold.
Yeah,
Things don't get cold, they get unhot.
Things always flow. This is important, folks, from hot to cold.
So if you open up the door and your mom says, "You're letting the cold in," you very politely tell your mother, "Sorry, Mom, I'm actually letting the heat out." But you'll probably get grounded or yelled at or something. So I wouldn't recommend that.
So if you're standing in the door and it's open, the heat will always flow out of the house, assuming the house is warmer than the outside.
Usually is up here.
And where we live, at a cold climate, that's usually the case. And so heat flows always from hot to cold, never the reverse.
Yep.
Okay.
Alrighty.
So we've said that. All right. So
ooh, delta H.
Hold on. No, I think we forgot something.
Okay.
Yeah, there's 2 ways that heat can be involved.
Oh, yes.
It can flow in one of 2 ways in a chemical reaction.
In a reaction. Endothermic. Endo means in. Thermo meaning heat. So the heat goes into the reaction. Now we talk about this when we talk about systems and we talk about surroundings. So energy is flowing into the system from the surroundings. Okay, we're not making heat. We're not creating it anywhere. It's going from one place to another.
So if I have a box right here, and this is sort of defined, it's going to be kind of weird, folks. This is called the system. Okay, the system in chemistry land is almost always a chemical reaction.
Right.
And so energy can either flow into your system, we're kind of think of it as a box. All right, and that is considered endothermic. You could. This would also be like inside of a house or your body. All right, an endothermic reaction, for example, would be as heat's being added to my body when I'm warming up after a cold day or something like that next to the fire.
Okay.
Okay, and then the opposite is true. If I have my box and then energy flows out of it
That's going to be exothermic. Exo meaning out, so it's going out of the system. So we're defining everything in relationship to the system.
This is considered, the box is the system here, and out here in this Never Never Land is the surroundings. So we have a system and we have a surroundings. You know, you could also think about this like with a human body. So inside of your body, as you're standing there, chemical reactions are taking place.
Yes.
So if you eat that Snickers bar or whatever it is, and then you eat that, those chemicals in the Snickers, they're not.
Snickers.
They can make you sick if you eat too many of them. The chemicals in the Snickers bar, which is sugars, C6H12O6. Ish, yeah. Those chemicals break down and they produce energy. They also produce carbon dioxide and water and such. But that energy then goes in your body, and that's what keeps your body warm.
Right, and that's why you radiate heat. That's why you have a temperature.
Yes. So, and also you can use that energy to move your muscles.
Yeah.
And to walk and talk and do the things that you do.
Yeah.
Okay.
All right.
There is a second or definition we need to kind of talk about. There's this thing called enthalpy. Enthalpy is something that we call and we measure as delta H.
Yes.
So delta H, what is delta H?
That is the change in of our heat in our system.
So it's a change in the heat of the system. Now there's two ways that heat can be involved. We just said exothermic and endothermic.
Mm-hmm.
So if delta H, actually we indicate there's actually no such thing as negative energy.
Right.
I've learned this in my motivational speaking.
Negative energy?
Negative energy.
Yeah, we want to block the negative
block
energy.
the negative. But you know, as
exactly.
a scientist, I can't use that term because there is no such thing as negative energy.
Now, when we put a negative sign with delta H, what we're referring to is the direction that it is flowing in relationship to the system. So if it has negative delta H, the energy is flowing out of the system. And as we learned, that is exothermic. If delta H is positive, the energy is flowing into the system. And we call that endothermic.
So, yeah, exactly, Mr. Sams. So it's important on these things, and we're going to spend a whole other chapter later on in the year learning more details about this.
Yeah.
But it's very important. The signs of delta H are very, very important. Positive energy flows in, negative energy flows out.
Yep, and you sometimes are just given a number, and you need to determine what the sign is going to be based on how the problem is phrased, and we'll talk more about that later.
All right. Now, delta H is a number. We love quantifiable numbers, and there are actually 4 ways that you can calculate delta H. And so you're going to just sort of fill this out. And we're going to learn a couple of the ways in this particular podcast or in this particular unit. The first one we're going to say is called calorimetry. It's like colorimetry, calorie. It comes from the word calorie. And so measuring calories. And you, of course, if you eat that Snickers bar, it has a number of calories in it. We can also use what we call Hess's Law version 1. And then there's also Hess's Law. You just write these down, and then we'll talk about them as they come, version 2. And then the last way is using bond energies. And frankly, folks, we're going to learn how to do the first 3 in this unit. And the bond energy one we can't really do until we learned about bonding.
Bonds.
All right. So that takes us now to a definition. Specific heat is an interesting concept.
Yeah.
It is the amount of energy it takes to raise 1 gram of a pure substance 1 degree
Just
Celsius.
as a vocabulary note, sometimes specific heat is also referred to as specific heat capacity.
Yeah. So let's say I have 1 gram of water. So if I have 1 gram of water, the amount of energy, so if I then take and I put a flame underneath this, red probably is a good color for flames.
Yes, very good.
And as the flame
Nice
goes
flame.
in there, yeah, there's my flame. Woo, flame. Okay, as that energy flows into my 1 gram of water, and let's say this is at 19 degrees Celsius, and if I can raise it up to
20 degrees Celsius.
20 degrees Celsius, then it will get the amount of specific heat.
Right.
For water,
it's the amount of energy it takes to raise it 1 gram of water 1 degree Celsius.
And the symbol for specific heat is a C.
Yes.
And so we
usually a lowercase c.
that is a lowercase c.
Yeah.
Yeah, well, that is a lowercase c. It's supposed to be. And the specific heat capacity of water is 4.18, and that's joules per gram degree Celsius. So it takes 4.18 joules to raise 1 gram of water 1 degree Celsius.
Yes, and that's actually relatively high as far as specific heats are concerned. Water has this amazing ability to be able to absorb and release energy without changing temperature. And that's actually a very good thing for you, because if it didn't and you went out into the sun,
You would boil.
your temperature would get really, really hot and you would boil, and that's bad.
You would not want to boil. It would boil your bones, your blood.
Yes.
And that would be very bad.
That's bad. We don't want that.
Yeah, and water has a very, very high specific heat compared to most things. That number 4 does not look very high,
No.
but it is very high.
Compared to like 0.2
One.
something or
Yeah.
whatever, or for some metals.
And so here's something that's kind of a weird oxymoron here. The lower the specific heat, the...
Greater the temperature change when heated. Good example of that would be a metal.
If you take a metal, you probably not in your car, Mr. Sam's, on a hot sunny day when you lived like in L.A.
Oh, yeah.
And then you probably you have a black car. Your friend had a black car.
Yeah.
What happened there?
It was pretty toasty.
Yes.
Yeah, my friend had a black Mustang, and it was like 115 outside, and you couldn't go near the thing because you'd about burn your hand off.
Yes. So you've probably ever been in that place that some things raise their temperature really high, and you burn because the temperature's so high.
Yeah.
But the same amount of energy went into that as, say, the lake that was right next to it, and that didn't heat.
That didn't change
much.
at all. No.
All right. And the higher the specific heat, the
lower the temperature change when heated.
The lower the temperature change. When
Yeah,
you
that was the nice thing about it in LA too. The closer you got to the coast, the more temperate the climate was. It didn't get nearly as hot or as cold because the water kept things nice and...
I happen to have an analogy for you, Mr. Sam.
Oh, please.
Let's
share with
just
us.
say that you're at the side of your...
Can you make it a motivational analogy?
I think so.
Please.
I do triathlons, and there's like these swimming... We swim in a triathlon, which is a motivational thing to do. I'm motivated to swim fast, okay? And so let's say you are here, and you are... let's say your name is Michael Phelps.
Ah,
He's a
I've heard of
famous
him.
guy. Michael Phelps.
Mickle.
I just spelled his name wrong, I bet. Okay, but Michael Phelps has decided to go swimming in this tiny little swimming pool. He never would do that. But let's just say he decides to walk onto the concrete. It's an extremely hot summer day. And what happens when he hops on here? It hurts my toes! He's complaining. Okay, I doubt he would complain, but we'll pretend he complains. Because you see, the concrete is made of, the deck is made of concrete.
Yeah.
And concrete has a...
Low specific heat.
So the temperature is very, very hot.
Yes.
So if he were then to dive into the water and swim his miles and miles in the water, what would happen?
Well, he's going to cool off because the water's not nearly as hot as concrete is.
And why is the water not as heat? It's the same sun is hitting both the concrete and the water.
But with the higher specific heat, it's going to be able to absorb a lot more energy with a very small temperature change.
Yes, so the temperature change is very small. Period there. Okay? So
Yep.
that's the key thing there. Okay.
Swim.
So what do we measure delta H with? What are the units on delta H?
We either usually measure it in joules or kilojoules.
All right, so the delta H, the units, are typically kilojoules, actually per
mole.
So it's per mole of a substance.
Yep.
Sometimes it can be per gram of a substance. And then you've got to watch the sign. The sign just means the direction of the energy flow.
Yeah,
So
watch
that's
the joules and the kilojoules things. Keep an eye on those.
Okay. And, we have forgotten one other thing here.
What did we forget?
This is what we forgot. We forgot the equation.
Oh, the equation, yes.
Yeah, the equation that solves for heat energy. And this is very important. Here's an equation you want to write down. Q is equal to M times C times delta T.
Yep.
Where M is the mass of the substance. Could be 100 grams of water, or 1,000 grams, or 1,000,000 grams of water.
Or
C is
50
the specific
kilograms
heat.
of Michael Phelps.
Yeah. And delta T. Now, what's that little triangle? That
Delta means
mean?
a change.
Change in the temperature.
Temperature.
So it's how much the temperature changes. So you would subtract. So if the temperature is 5 degrees and it goes to 10 degrees, delta T is
5.
5. 10 minus 5.
Yeah, sorry. I was thinking of something else. Mr. Bergman, why is it a Q? I thought we were talking about delta H.
Yeah, because when we do calorimetry, we have to solve for Q, because Q is like the energy.
And Q gives us joules.
Yeah, joules or kilojoules.
It's not joules per mole yet. You're going to have to divide by something by something's moles to turn it into kilojoules per mole if you actually want an actual delta H value.
So you're going to do some kind of a stoichiometric thing or
Right.
just a dimensional analysis to find moles. So basically what you do is you're going to take the kilojoules and you're going to divide by the moles to get your answer. So this is almost like an equation to solve for delta H. If you know one number and the other, you simply divide. Now the sign does not come from the mathematics.
No, it comes from
your brain.
Your brain.
You must use your brain to solve for the mathematics. So watch that. That really is a critical component. Okay, we have a couple of examples, mathematical problems that we're going to try and solve.
Okay.
So here it is.
You can read it in your handout.
You can read it in your handout. So I got some magnesium.
Yep, magnesium dropped into 125 milliliters of HCl.
All right, so let's just write the reaction.
Yeah,
Magnesium
please.
reacts with hydrochloric acid. It's like a stoichiometry problem, so we'll start with A.
Balanced chemical equation.
And it turns into what?
Well, it doesn't tell us, but we've already done our product prediction unit, so I'm assuming that you all can figure this out.
So the magnesium has a 0 charge. So
Yep.
you're going to want to go up to Mg2 positive.
Yep.
And so he went up. I still
Yep.
need to find somebody to go down.
Hydrogen's going to go down.
Hydrogen can drop down to
H2,
H2.
and we're going to have some chlorides left
leaves
over.
the chlorides left out.
Should we balance our equation?
And to balance this, of course, you would need a 2 here, and I believe a 2 here.
Yep.
And that is our equation. Now, what do we know, Mr. Sam?
We have 3.25 grams of magnesium.
3 1/4 grams.
We have 125 milliliters of hydrochloric acid. We have an initial temperature of the calorimeter at 18.5 degrees, and the final temperature is 25.6 degrees. And we're assuming the heat capacity of the calorimeter is 4.86 joules per gram degree Celsius.
So what we're going to do is we're going to try and figure out, well, delta H. And
Yep.
delta H is the kilojoules
Per
divided by the moles.
moles.
So we're going to use some of the information to find the kilojoules. And the equation you're going to use to solve for this will be the Q is equal to MC delta T, the MCAT equation, I like to call that. And then the moles, we're going to get from the moles of which?
Should be from our magnesium.
You're right. Now, how would you know that, though, Mr. Sam?
Let's see. How would I know that?
You would know that because you
I just
actually
know.
want
I don't know how I know.
You would have to do the one that is the limiting reactant.
There you go.
And you have plenty of hydrochloric acid and not
Yeah.
nearly as much magnesium.
Okay.
So let's do the Q equals MC delta T equation first, and then we'll divide.
Okay.
So what's Q, of course, is our variable.
Okay.
M is the mass. Now, what do we do for mass?
Mass. Well, since this is going on in a calorimeter, usually we're looking at the change of temperature of some water. And the thing that has the water in it is our hydrochloric acid.
And so actually, we actually need to add the total mass of the system, though, is the addition of these two. Now,
Correct. Because
even
once
though-
you throw the magnesium in there, it reacts, and that is part of the mass of the stuff.
But I can't add 3.25 grams with 125 milliliters.
No. But the nice thing is that hydrochloric acid is mostly water, and the density of water is 1.
So 1 milliliter is equal to 1 gram,
Yep.
and so that's 125 grams. So
Yep.
our total mass is going to be 128 grams. I'm going to not worry about the 0.25 from a significant
Sig
digit perspective. So our mass is 128 grams. So that's
Okay.
M. Now this
C is
specific
given to us.
It's
4.86 joules over grams degrees Celsius.
It's a little higher. Why do you think it's a little higher than 4.18?
Well, we're taking into account probably the cup that it's in, and
Yeah.
it's also the fact that it's not pure water, it's hydrochloric acid and has some magnesium and stuff in it.
And our change in temperature went from 18 to 25.6.
25, yeah. Oh, I should probably get my calculator.
5, 6.5,
7.1.
7.1.
Yep.
I almost got there. 7.1 degrees Celsius. So we just simply multiply 128 times 4.86 times 7.1, and that gives you,
That gives you 4417 joules.
and that's in joules. Now, the reason you know this is in joules, ladies and gentlemen, because this is joules right here.
Yep.
Now, we're going to take that. That is our number on the top. So let me create a new screen. So it's 4, what was it again?
4417.
44171. All right, hold on. 4417 joules, and I will then divide it by the moles.
Yep.
Now, how do I find the moles?
Well, we
Let's
have
go back.
grams of magnesium, 3.25.
So our grams of magnesium is our limiting reactant,
Yep.
and so we need to then take our 3.25 grams of magnesium, and we need to convert that to moles.
Using its molar mass, which is 24.3.
24.3 grams of Mg.
So we get 0.134.
0.134 moles of magnesium. Now that goes on my other screen here. 0.134 moles, and I get a whopping number.
Well, we do need to make sure we're in joules per mole.
Yeah, so what is it in joules per mole?
That joules per mole is 32962. 32963.
That's a pretty big number,
That
Mr.
is a
Sims.
pretty big number.
And that's in joules per 1 mole.
Yep.
We'd like at this point to convert to kilojoules per mole. So there's 1,000 joules in 1 kilojoule, and the joules cancel. And I'm going to probably just say
33.0, probably from a sig standpoint.
3.0 kilojoules. Now that is
Per mole.
actually per mole is not the correct answer, Mr. Sims.
What?
Yes. Why is that not the correct answer? It is because we have not considered the sign of delta H.
Oh,
because the temperature went from 18.5 to 25.6. The temperature rose.
The temperature of the water went up, which tells me that the reaction that is happening in the water released energy.
So therefore, this is where we need to then say, oh, the
Negative
sign is negative. So the math did not yield us the
No.
answer. So the end of these problems, you've got to always ask the
Yes.
question, is it endothermic? Then it would be positive. Or exothermic, like this example, which is negative. Generally speaking, there are exceptions. If the heat temperature goes up, it's going to be exothermic.
Right. Now be careful, because the water is the surroundings.
Yes.
Okay? The system is the magnesium and the HCl, and it's happening in the water. So the water is the surroundings.
And that's what's warming up. So
Right.
this.
So be careful. We're
so
measuring the
energy is
temperature of the
here's the
surroundings.
reaction, and the energy is flowing out of this into the water.
Yep.
And it's really important to kind of think that through to solve these problems, okay?
You'll get
And you're going
used
to actually do an experiment just like this in class with actually these same chemicals. All right, and then we're going to do one more here. Okay, before we do this example, guys, let's actually talk physically how this is done. I realize I actually skipped a screen, and if you go back, you'll see this cool picture. This is where I put the heat equation.
Yes. That's
Q
what I
equals
missed
MC delta T. This is what you were supposed to put here. We did this out of order, and I couldn't figure out what I had done. Okay, so this thing called calorimetry, we use a calorimeter. And this is an example right here of a calorimeter, this picture right here. And it's a device here. You can see this would be the liquid, probably water. You got a stirring rod right here. You can see that right here. And the reaction is taking place inside of this thing.
Now this one's actually called a bomb calorimeter.
Yes.
This is how they determine how many calories are in your food.
Yeah, basically they take the food object, the Snickers bar or whatever, and they put it right here, and they burn it. They
pump that chamber full of oxygen and they ignite it.
Yeah, they have an electrical
and it literally burns and blows up in there. That's why it's called a bomb calorimeter. But it's made so well that it doesn't blow apart into parts. All the heat
goes into the water.
Yeah, all the energy actually is just turned into heat.
Yeah.
And that goes into the water. You measure the temperature change. You can figure out how many.
Now, that's a kind of expensive device.
Yeah.
You can also get, we call a coffee cup calorimeter.
Yes.
And a coffee cup calorimeter is uber cheap. You get a styrofoam
coffee cup, hence the name.
And then you...
and if you want to go high-tech, you can nest 2 of them together.
Yeah, we can get 2 of them together. Ooh, and now you've got from
Super
20
insulation.
cents to 40 cents.
Yep.
Okay, and so then you have your reaction take place. So like the example we just did, if this was, say, hydrochloric acid, and you'd put a little strip of magnesium in there, and then the reaction would take place.
And you just have a thermometer sticking out in there.
Thermometer. And sometimes if you want really high-tech, you would put another styrofoam cup on the
top of it.
And it would be like a cap.
Wow.
And it would be, now
60
cents.
I always used a piece of cardboard at my last school. 2 coffee cups and a piece of cardboard.
That is high-tech. Now, amazing.
Nothing but the finest in public education, folks. That's right.
Indeed. But even though that sounds kind of cheesy, the reality is this yields pretty good results.
It works wonderfully.
You actually usually can get within about 5% of the actual answer compared to this expensive bomb calorimeter that we showed you just a moment ago.
Yeah.
So these coffee cup ones, though we deride them a little bit, they actually are pretty good. And that's how we would do an experiment like this.
Yeah, it looks totally chintzy and cheap, but it's great. It gives great results, which is why we do it. And every chemistry class in the country that I've ever known of does this lab.
Yeah, and so we will, of course, do it ourselves.
Of course.
And then lastly, let's do this last example, because you have this specific heat. And so this is a particular problem where we are going to take our expensive or whatever, calorimeter.
Yeah.
And then what we have in here is we have some cold water. And then what we're going to do is we're going to take a piece of metal that's very hot.
Yeah.
Not very, very hot, but hot.
Hottish.
And we're going to drop it into the water. And what's going to happen to the water? When
the
you put a
temperature
hot
of
piece
the
metal,
water is going to go up, and the temperature of the metal is going to go down.
And the metal will go down.
And the interesting thing is the temperature that the water goes up to and the metal goes down to is the same Temperature. That is very, very, very,
Important.
very, very, very
Very what?
important.
Oh, okay.
Yes.
Okay, so
And inspirational.
we must be inspirational all the time. As students, it's important to be inspired. Are we inspiring you?
Yeah, I certainly hope so.
I hope we are inspiring you to become amazing, inspirational speakers. Actually, scientists would be
Chemists,
better.
yeah.
Chemists, yeah.
We don't want them to be inspirational speakers. That's going to cut into your market.
That's true. I
Yeah.
want them to be scientists.
That's right.
Maybe I can be an inspirational speaker to scientists.
There you go.
There we go. Because I'm a
Yeah.
scientist and I know those things, so maybe I have a better connection with those brainiac types.
Perhaps.
Okay, so here's the problem. What you're going to do is that we're going to take a sample piece of copper. So actually, this piece of metal right here, let's just call it copper.
Right.
And let's kind of write down what we know.
And by the way, guys, when you get to a problem like this, draw a picture.
Yeah,
It is so helpful to draw a picture.
actually, I'm going to draw a new picture so I can label the part. So the
Yep.
piece of copper, this is the copper, has a mass of,
Mass of 46.2 grams.
and then in this I have some,
And it has a temperature too, 95.4 degrees Celsius.
95. How would you get it to 95.4?
I would probably just put it in some boiling water.
Yeah. Well, why shouldn't it be 100 degrees Celsius?
If you're at sea level, maybe.
But where we live, of course, the boiling point
About
is actually
92-ish.
92. So this would be somewhere maybe like a Denver condition, which is actually where I think I got it from. Okay, and then we know some other water.
It goes into the calorimeter. There are 75 grams of water. The water's at 19.6 degrees Celsius. So we drop it in, and they both come to a final temperature of 21.8 degrees Celsius.
So, folks, this is a super easy experiment.
Right.
You take
And we
a
want
piece-
to find the heat capacity of the copper.
the copper is hot. You just have it in some boiling water, so you probably have a hot plate or something like that.
Yep.
And then you have a beaker on top, and your piece of copper is inside it. And once it's boiled, you take it out, probably a pair of tongs, it'd be kind of hot, and you drop it into here. And then it's going to raise the temperature of the cold water a little bit.
Yep.
But the thing is you can find the specific heat of the metal. Now, how do you find the specific metal? You have to make a very important assumption.
Yes, we have to assume that all of the heat from the metal was transferred to the water. And that's a pretty safe assumption because styrofoam is a really, really good insulator. It's not going to absorb much of that heat.
Actually, in this experiment, the big issue in terms of the transfer of the heat is that you lose some heat in transferring it
Yes,
to the water.
so go fast.
So you just transfer it as quickly as possible with your tongs. So if you think about it, there's actually two Q's here.
Yep.
There's the Q of the water, and there's the Q of the metal.
And those are equal to one another,
And
except
this is equal to MC delta T.
one of them absorbs
and
the
this
temperature.
is MC delta T. But
And
this
one
is
of
a
them
different mass.
loses it.
This is the water's mass. This is the metal's mass. But we're going to say that these two Q's are the same. So we can write that MC delta T of the metal is equal to MC delta T of the water. Actually, I switched my deals. Oh, well, that's fine.
Either way.
So
Yeah.
now we're going to plug this in. So what is the mass of the metal?
Is 46.2 grams.
46.2 grams.
We don't know what C is.
So the specific heat of this one is C. That's our variable, our X, if you will, if you want to be more algebraic. Now, this is a little tricky. What is the delta T of the metal?
Well, the metal went from a hot temperature to a low. So when you do a delta, you take the final minus the initial? No, initial minus final. Why am I confusing myself?
You know, I don't even think about initial minus final. I just always make an absolute value. It's
Okay,
just going to go
that
from,
works too.
It went from 95 to 19, so it's just subtract
Actually, it went
the
to
big...
21.8.
Oh, it went to 21.8.
Yeah.
Sorry about that. So you're going to take 95.4, subtract 21.8.
73.6.
70-some degrees. 70 what?
73.6.
So this changed to 73.6.
Yeah.
It's very important. A lot of people are going to get this mixed up. The metal was hot and it got cold.
Yes.
Okay. And then we can do the mass of the water.
75 grams.
75 grams. Now, water is something where we do know its specific heat.
4.18.
It's just the 4.18 joules per gram degree Celsius.
Mhm.
And the change in the temperature of the water, now it went from 19.6 up to 21.8.
2.2 degrees
It
Celsius
went up
delta.
just a small degrees, 2.2 degrees Celsius. Small because its specific heat is high. You simply now do your algebra and you solve for C. You divide both sides by 46.2 and 73.6, and your specific heat of metal is going to be a small number,
0.20.
0.20 joules per gram degree Celsius. And this would be the specific heat of copper.
Mhm.
Okay. at least from this example. I'm not sure that's exactly the correct answer.
Yeah.
But experiments are never give you totally exact. Notice also that this number right here, the 0.2, is a very small number compared to 4.18. But because that's a metal. Metals heat up very rapidly, given the same amount of energy because they have low specific heats. All right. So,
all right.
You know, I've been working on my quotes some more.
Oh, do you have some more for us?
I do.
All right.
Son, if you really want something in this life, you have to work for it. Now, quiet. They're about to announce the lottery numbers.
Ah,
That's
nice.
Homer Simpson.
So work hard and get lucky.
Yeah.
Okay.
You know, a computer once beat me at chess. You know that?
Really?
Yeah, but it was no match for me at kickboxing.
Ah, yeah.
Yeah.
They can't kick back.
Hey, I say all that, and
that was very motivational.
Motivational, indeed. I am the motivational king of the world. Hey, tell you, I will end with a famous, actually profound quote.
Okay.
One of Mr. Bergman's
Profound
famous.
us.
Okay. And this is from Teddy Roosevelt.
Okay.
You know who he was?
The first Roosevelt, early 1900s-ish.
Yeah, he was a president.
He was
of the
a
United
president.
States.
Yeah.
He's now passed away. But he said this. He said, it's not the critic who counts, not the man who points out how the strong man stumbled, or where the doer of deeds could have done better. The credit belongs to the man who's actually in the arena, whose face is marred by the dust and sweat and blood, who strives valiantly, who errs and comes short again and again, who knows the great enthusiasms, the great devotions, who spends himself in a worthy cause, who at the best knows in the end the triumph of high achievement, and who at the worst, if he fails, at least he fails while daring greatly, so that his place shall never be with those cold and timid souls who know neither victory nor defeat.
Wow.
Very profound.
That is inspirational.
It really is.
Quite.
It's one of those things I like to live by. Live with passion. You must live with great passion, whether you play the harmonica or whether you talk funny like you have Russian accent or whatever it is.
Yeah.
Okay.
The guy punching the numbers in the calculator on the podcast.
The podcast number
Passionately punching the numbers.
So we hope that you are enjoying the chemistry discussions. Have a great day, and we will see you in class or more on the internet. Bye-bye.
Bye.